Hey everyone, and welcome to This Explainer. I am absolutely thrilled you're here. Today, our goal is to build a super clear, working mental model of the most important machine learning algorithms used in the world today. And you know what the best part is? We are going to do this without relying on a single overwhelming equation or getting bogged down in heavy math. We're focusing purely on the intuition behind these incredible tools. By the end of our time together, you won't just know what these tools are, you'll actually have a rigorous mental framework for exactly when to deploy which algorithm.
Okay, let's dive into our roadmap. We've got 6 key areas to hit. First, the machine learning umbrella, followed by supervised learning basics. Then, we'll get into neighbors, margins, and boundaries. After that, we'll explore trees, forests, and ensembles, unlock the power of neural networks, and finally, wrap up with unsupervised learning and beyond.
All right, Section 1, the machine learning umbrella. Let's look at the big picture. Before we break down the specific tools, we really need to understand the overarching field. The fundamental paradigm shift here is moving from explicit programming to algorithmic inference. Think about it. Instead of hard-coding rigid rules to tell a computer exactly what to do in every single possible situation, we just feed the system examples. We allow it to autonomously extract patterns and logic so it can make decisions entirely on its own. It's literally a whole new way of solving problems.
Broadly speaking, this entire landscape is divided into 4 main territories. You've got supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. Having this whole map in the back of your mind is super helpful before we zoom in and unpack the largest compartment first.
Which brings us to Section 2, supervised learning, the basics.
So, in this compartment, we basically have a cheat sheet. We're given a data set where we already know the correct answers. We have inputs, like a house's size and location, and a known output, like the house's actual price. The model learns from these labeled examples to predict labels for new data. But within supervised learning, you face a fork in the road. Are you predicting a continuous number or a specific category? Regression gives you the continuous number, like that house price. Classification, on the other hand, sorts things into distinct buckets, like filtering an incoming email as either spam or not spam.
Let's talk about predicting a number first. The most basic regression algorithm is linear regression. It tries to fit a straight line that best describes the relationship between the inputs and the output by minimizing the square differences between predicted and actual values. So, say we plot a bunch of data. A linear regression model might discover a quirky little pattern. For every 1 unit increase in shoe size, a person is, on average, 2 inches taller. We just fit a straight line that best explains that relationship. Now, real life is rarely that simple, so we can always add more features like gender or age to improve the model.
But here's a great question. What if we need to predict a category instead of a number? Straight lines are great for continuous numbers, but they kind of fall apart for classification. That is where logistic regression comes in. Instead of fitting a straight line, it uses a sigmoid curve to estimate probabilities. Say we have someone who is 180 centimeters tall and weighs 75 kilograms. The model doesn't just say a rigid yes or no to category A. It calculates a probability. It might say, hey, there's an 80% chance they belong to category A. If that probability is over 50%, boom, we classify them as category A. This ability to output a nuanced probability is exactly what makes logistic regression a total cornerstone of risk assessment today.
Moving on to Section 3, neighbors, margins, and boundaries.
Here, we're completely abandoning those simple equations and straight lines for much more complex ways to divide up our data. Our first tool here is k-nearest neighbors, or KNN. What's absolutely fascinating about KNN is that it's fundamentally a lazy algorithm. It doesn't actually try to learn a math equation at all. It literally just memorizes the training dataset. Imagine a new person drops into our dataset with a height of 175 centimeters and a weight of 70 kilograms. If we set our k value to 5, the algorithm just looks at the 5 closest people in the dataset. If 3 of those 5 are male and 2 are female, the model uses a simple majority vote and predicts male. It simply says, well, you're most similar to these 5 people, and most of them are male.
But of course, there's a catch, and it's all about choosing that k value. If k is too small, say k equals 1, the model just copies the single nearest data point. If that one neighbor happens to be a totally unusual outlier, your prediction will be 2. This is the classic trap known as overfitting. The model memorizes the training data a little too closely. On the flip side, if k is too large, the model averages over way too many points, ignoring local structures and becoming way too smooth. We call that underfitting. Finding the right balance for k is a real art.
So what if you don't want to just rely on the neighbors?
What if you want to draw the absolute best, most robust dividing line between your categories?
Well, the crucial point here is support vector machines, or SVM. Imagine you're plotting data to classify animals into dogs and elephants based on their weight and nose length. Sure, lots of lines could separate the dogs on one side from the elephants on the other, but SVM chooses the specific line that leaves the maximum possible distance, which we call the margin, between the two classes. A wider margin means the boundary is far more robust against noisy data. And here is the absolute genius of SVM. Once that boundary is found, only the data points closest to it actually matter. We call those the support vectors. The rest of the data could literally be deleted, making SVM incredibly memory efficient.
Okay, but we hit another snag. What happens when simple straight lines completely fail? Suppose your data points are arranged in a circle, right? You've got one class inside the circle and the other class outside. A straight line simply cannot separate them. No way.
This is where we use an amazing math technique called the kernel trick. Without getting bogged down in the math itself, kernels allow SVM to transform the data into a higher dimensional space. Imagine physically lifting those two-dimensional circular points up off the page and into 3 dimensions. Suddenly, what looked like an impossible puzzle in 2D can be sliced right down the middle with a single flat plane in 3D. It's such an elegant mathematical loophole.
Section 4. Trees, Forests, and Ensembles. This compartment is all about sequential questions and the incredible power of group voting. A decision tree is brilliantly intuitive. It works by splitting data step by step using a sequence of simple yes or no questions. For example, if you're predicting a patient's risk level, the first question might be, is age greater than 50? The data splits, and the process continues until it creates final decision points, which we call leaves. The ultimate goal is to make those leaves as pure as possible, minimizing misclassified points along the way. However, a single decision tree can easily overfit and be way too sensitive to small changes. So what do? We combine many simple models into an ensemble to create a much stronger overall model. Let's compare 2 famous ensemble methods. Random forests use a technique called bagging. It trains many independent trees in parallel on different random subsets of data and features. This prevents them from making the exact same mistakes, and the final output is just a majority vote. On the other hand, boosting algorithms like gradient boosting and XGBoost train trees sequentially. Each new tree specifically focuses on correcting the mistakes made by the previous tree. Both are incredibly powerful ways to stop overfitting, which makes ensembles the go-to strategy for winning machine learning competitions today.
All right, Section 5. The power of neural networks.
Now we're entering the advanced tier of supervised learning. In simple regression, we map features to an output using a straightforward formula. Neural networks completely change the game by adding hidden layers of interconnected nodes, often called neurons, right between the input and the output. Instead of us manually deciding which features are important and feeding them in, the network relies on these interconnected layers to extract what's important from the raw data all by itself. It uses calculus and linear algebra to automatically adjust weights and biases. Each layer transforms the data slightly and passes it on to the next. Let's see how this builds when we stack multiple hidden layers, unlocking what we call deep learning. The network begins to learn increasingly abstract representations. In image recognition, for instance, the raw image goes in, and the first layer just finds simple shapes, like little lines and curves. The next layer combines those to recognize bigger parts, maybe some stripes. And the final layer puts it all together and successfully identifies, hey, that's a zebra. This automatic, step-by-step feature extraction is exactly why deep learning absolutely dominates image and speech recognition today.
And finally, Section 6, Unsupervised Learning and Beyond.
Let's open up the final compartments of our toolkit. These are designed for scenarios where we simply do not have fully labeled datasets. When we lack labels, algorithms have to find hidden structures entirely on their own. Clustering is a great example. It's like asking a child to group a massive pile of pictures by similarity without actually giving them any categories. Dimensionality reduction, like PCA, acts as a data simplifier. It keeps the useful information and drops the high-resolution noise. Because honestly, you don't need a massive high-res picture just to identify a cat. And then we have semi-supervised learning, which is a brilliant hybrid. Imagine you have 10,000 medical images, but doctors only had time to label 500 of them. The algorithm leverages that small labeled batch to guide its understanding of the massive unlabeled portion. And that brings us to our final paradigm, reinforcement learning. It's completely different from the rest. It learns by interacting with an environment, receiving rewards for good behavior and penalties for bad behavior. Honestly, it's very much like training a dog over time. The agent constantly updates its strategy to maximize its total future rewards. This is the very core idea driving game-playing AI, advanced robotics, and self-driving systems. So, I'll leave you with this to ponder. As these autonomous, reward-seeking systems become more complex and more capable, how profoundly will they shape the future of real-world AI decision-making? Thank you so much for learning with me today. Keep exploring.